I'm not sure I'm going to put this last question on the exam, but I'm going to do it here on the practice exam. So it's asking you to find the absolute maximum and minimum values of this function on a certain closed interval. So we're going to learn how to do that in class. We haven't had the lesson as of me talking right now. But we're going to use a method called the closed interval method. And so this method is pretty easy. So the method has a couple parts. The first thing we need to do is find all critical numbers. Find all C such that either f prime of C is 0 or f prime of C does not exist. And there's this little detail that sometimes matters, usually it doesn't. C has to be a number for which f is actually defined. So C is in the domain of f. And so that's what a critical number is. So this is the definition of a critical number. Critical number. And now let me just actually find them. So we need to look at f prime. Pick the wrong thing again. Okay. Oh man, I just ripped f's head off. Okay. I'm going to try to do this a little better. Now let's, just to be clear, the function is f of x equals x over x squared plus 2, 1 that is, 1 being 2. So what is f prime? It's the quotient rule. So first thing I do is take the derivative of the top, which is 1, right, x squared plus 1, minus, now I leave the top alone, and times it times the derivative of the bottom, which is 2x. And now I square the bottom, and so I get x squared plus 1. And great, so I actually have to do some algebra here. So that means that I'm actually going to have to simplify, which I almost never do. But look, it says that I'm going to have to find, I'm going to have to basically solve the equation that comes from setting this stuff equal to 0. So to make that easier, let me clean it up a little bit. So just look at what happens on the top. Alright, when I clean up the top, I am going to have a couple x squareds. This is the same thing as x squared plus 1 minus 2x squared. And that will allow me to have just 1x squared instead of 2. Actually, I forgot to write this. Okay, so x squared plus 1 squared. Okay, and now this becomes 1 minus x squared over the bottom, which is x squared plus 1 squared. Okay, and now when we're trying to find the critical numbers, we need to find the places where either f prime doesn't exist or it's 0. So let's just look and see. Alright, so look at the domain of the function. The domain of the function is going to be everything, because what does the domain mean? It means like what can you put in to get a real number out, and because the square down here will always make the bottom positive, I don't have to worry about 0 in the denominator. So if I can find, I don't have to worry about this weird clause. In other words, I can just ignore this like I wanted to in the first place, because everything is in the domain of f. Now let's think about this green bubble here that says that the derivative has to be 0. Alright, so let me set this equal to 0. Now, I know this looks scary, but you have to remember that when you set a fraction equal to 0, the only way it can actually be 0 is if the top is 0. Okay, so the question here is, when is the top 0? So let me write that off to the side. When is 1 minus x squared equal to 0? Much easier, right? This is just 1 equals x squared, and so this is x equals plus or minus 1. Easy as pie. Alright, so that just told me two critical numbers. So I have this in my, whoa, I have that in my bucket of critical numbers. I have two things in there so far. Maybe we could just write crit numbers here. And so that is, we have 1 and -1 so far. Now let's see which other ones we get by looking at the second property of a critical number that says it's also a critical number if the derivative isn't defined. So also, since this is a fraction, we actually have values where that is the case, I imagine. I haven't thought about it. Oh no, I lied to you. Look, it's still the case that anything you put in here doesn't make 0 in the denominator. So 0 in the denominator is what gives you these other kinds of critical numbers. But since there is a square here, I'm never going to get 0 in the denominator because positive plus 1 is positive and there isn't anything bad that can happen. So these are actually the only critical numbers. Alright, so I have just completed phase A of using the closed interval method. The first thing you have to do is find the critical numbers, or as I like to call them, the crit numbers. And what else do you have to do? You just compute, you check the values of the function. So now I'm just going to check values on critical numbers and endpoints. So critical numbers, it's a numbers sign, and endpoints. And you're saying, what is he talking about, endpoints? So the closed interval is actually around here somewhere. It's this interval right here. So it has endpoints. You know, one endpoint is 0 and one is 2. So I have to check that in a second. But, okay. So by check values, I mean plug those things into the function. So we want to look first at, let's say, let's just look at f of 1. Okay, so what does that turn out to be? That turns out to be 1 over 2 is 1/2. It's 1/2. Okay, now let me check f of -1. And what happens? I'm going to get -1 over 2 is -1/2. Okay, and so the last thing to do is to check the endpoints of the interval. So 0 is 1. And what happens when I plug in 0? I get 0 over 1 is 0. Okay, so 0. And the other endpoint, I wish I could make those nice smooth zeros in real life. And so what happens when you plug in 2? I'm not even going to go up there again because we all know that it's x on top, so that gives me 2. And I've got x squared plus 1 here, so it's 5, right? And let's just do a sanity check. So what happens if I plug in 2? I get 2 over 5, yes. Okay, so now we're at the very last phase of using the the closed interval method. And so once you have all these things, remember what we're doing. We're looking for the absolute max and the absolute minimum value. So the absolute max value is just the biggest one that appears here. And if you think about it, it's this one. So this is, so what is, let me just say it. So the absolute max value is 1/2. And it happens at x equals 1. Okay, alright. And so the way you find the absolute minimum is just exactly the same, except you look for a small number instead of a big number. So what's the smallest number here? It is this, right? -1/2 is the only negative number. So let me just write out what this means. It means the absolute max value is -1/2, and this happens at x equals -1. And we've solved the problem. Okay, so we found the biggest and the smallest value that this function takes on this closed interval, and we also gave the x values where it actually happens. So I don't know who could ask for anything more than that. And I guess we're done with the practice exam.